Ladies and gentlemen, good morning. I'm here on behalf of the Society of Petroleum Engineers to present a lecture which is part of the 2004-2005 SPE Distinguished Lecture Series. The series is made possible by the SPE Foundation. I would like to thank our society, the SPE Foundation, but I also will add my thanks to my employer, Louisiana State University, for giving me the opportunity to participate in this important program. The title of my presentation is Low-Cost Methods for Improved Oil and Gas Recovery. It is usually perceived that improved oil and gas recovery is a costly proposition. However, several low-cost improved oil and gas recovery processes have been successfully tested in the field. The objective of this presentation is then to make these methods and their concepts known to the audience. Detailed discussions of these topics are available in several SPE publications. The processes that I'm going to discuss today are the double displacement process of improved oil and gas recovery using air injection, single well cyclic CO2 injection, normally referred to as the Huff and Puff process, co-production of oil and water from water-drive gas reservoirs, water flooding of low-pressure gas reservoirs. This is by no means a comprehensive list. There's many more processes that will fit under the title. However, I selected this four because Louisiana State University researcher participated in the conceptual definition of this method, hence my familiarity with them. I will start with the double displacement process. You can find detailed discussion in SPE 35360 and SPE 39462. This figure depicts the initial saturation in a water-drive reservoir where the oil zone still has its initial oil saturation. At the conclusion of the primary phase, where all the wells are producing at high water-oil ratio or shut-in, the water-swept oil zone, depicted here in light blue, still contains significant amount of oil. It is that oil that is the target of this process. The double displacement process consists of injecting gas at the top of the reservoir. The gas will displace first the mobile water that encroach in the reservoir, and when the gas comes in contact with the oil, the part of the oil will become mobile again due to the alteration of the interfacial and capillary pressure conditions in the reservoir. This newly mobilized oil will drain downwards due to gravity, where it can be captured down dip. If gravity process is deemed to be slow, we could start producing up dip, reversing the pressure gradient, allowing the aquifer to re-encroach into the reservoir, displacing ahead of it the mobilized oil. This process is referred to as the SCWD, or the second contact water displacement. The feasibility and the potential recovery of such a method was first demonstrated in the lab using core displacement. This figure depicts two of these displacement using Berea sandstone, and as you can see, the oil saturation at the beginning of the displacement, or the beginning of gas injection, is 30-35%. That's the amount of oil remaining after water displacement. At the end of gas injection, one can see that the oil saturation was reduced, like in the green case down to 13%, and in the other yellow case down to 17%. This represents 50 and 57% of the water residual oil mobilization, which is significant. This process was tested in the West Hackberry field in the western part of the state of Louisiana. The purpose of this test was twofold. One, to demonstrate the feasibility of air as the gas to be injected. The operation problem associated with using air was successfully mitigated. The technology behind that is described in detail in the November 1997 issue of World Oil. I will show you here an example of the reservoir performance. You can see that before air was injected in July 1997, the decline during the primary phase, and you can clearly see the positive response to air injection. The area above the normal decline described here by the dashed line represent the incremental oil due to air injection. I would like now to discuss the single well cyclic carbon dioxide injection, or CO2 Huff and Puff. You have on the screen the number of SPE paper giving details of the process. The cyclic CO2 injection consists of 3 steps. First, the gas is injected in a well. The well is shut in, allowing an interaction between the oil and the gas. This step is usually referred to as the soak period. At the conclusion of the soak period, the well is opened, and normally we experience an increase in oil production. This cycle may be repeated if the economics is still favorable. The major recovery mechanism of this process are the swelling of the oil, reduction of oil viscosity, and decreasing of water saturation near the wellbore as the gas pushes the water away. These 3 mechanisms improve the mobility of the oil. Also at high pressure, oil components may vaporize and are recovered. And the injection would increase the bottom hole pressure around the wellbore. Hence, we will experience an increase in rate when the well is brought back on production. This process is attractive because of its shorter project life. It usually uses a smaller amount of CO2 compared to full-scale CO2 flooding. And most importantly, in reservoirs with poor inter-well communications, Huff and Puff may offer the only feasible process for incremental recovery. This is a typical performance of a cycle treatment. As we can see, after the decline we experience during the primary phase, in this case due to increase in water production, after injecting the CO2 and shutting in the well for the soak period, we can see a significant stimulation of the well. However, that stimulation is followed by a rapid decline as we are depleting the reservoir. Field implementation of cyclic CO2 has been successful in diverse reservoir environment. A database was created and was evaluated by LSU researchers to determine the key factors affecting the performance of the Huff and Puff process, and also to define an approximate, simple, predictive method that we can use to evaluate the process. This graph clearly shows that the incremental oil increases as with the volume of CO2 injected. This is no surprise. However, we need not to maximize CO2 injection. We have to design the volume injected to prevent interference with nearby wells. Over-injecting could affect the production, offset production, as is seen here, where that well is showing an increase in production during nearby CO2 injection. This could be positive or negative depending on who owns this particular well. This graph shows that everything being constant, the stimulation ratio, or the increase in production, is directly proportional to the thickness of the pay interval. The pay interval can be one of the critical screening criteria that will allow us selecting the best well or to apply this method. The incremental oil increases with the amount of oil that swelled. The higher the swelling factor, the higher the incremental oil production. The swelling factor depends mainly on the oil composition. The heavier the oil, the lower the swelling. So one can say that this process is more amenable to light oils. CO2 injection was first introduced as a miscible process. However, as you can see on this graph, that the cyclic process result in incremental oil at any pressure. However, the higher the reservoir pressure, the higher the incremental oil. Now let's discuss the effect of the soak period, or the length of the shut-in period. The longer we shut in the well, the higher the incremental oil. However, the longer we keep the well shut, the later we can reap the benefit of this process. You can see a cluster of points in the middle of the graph that suggest that an optimum soak period would be 30 to 40 days. The simplified predictive method, illustrated by this simple equation, simply states that the residual oil after CO2 injection is proportional to the residual oil after water displacement. The proportionality constant is the viscosity ratio, the ratio of the viscosity with the CO2 swelled oil to the viscosity of the oil before injecting CO2. This is an interesting equation. First, it is simple. Secondly, all the parameters you see there are readily available or can be obtained without much effort. This is a correlation between the observed incremental oil in the field and the calculated incremental oil using this simple method. As you can see, this is a very encouraging correlation. The 2 points that clearly fall off the 45-degree line were traced back to mechanical failures of the well. Let's now switch to gas recovery. Let's talk about enhanced recovery from water-drive gas reservoirs. Depletion-drive gas reservoirs are characterized by a high recovery factors in the high 80s and up to the 90s. The reason is the recovery is limited by the minimum reservoir pressure we can realize in the reservoir. We have control on that. In the water-drive gas reservoir, the recovery factor is much, much lower. Actually, in some unfavorable cases, it could be in the 30s. The recovery factor is controlled by the reservoir properties, geometry, and heterogeneity, which most of the time we have no control on. The reason for this low recovery factor is substantial amount of gas is bypassed by the advancing water. The bypassing occur on a microscopic scale, as you can see in this schematic of a porous space after the water passed a part of the reservoir. A substantial amount of gas which is depicted here in red, is present. Now, one can say, but this, on a volumetric scale, this is not quite high, but let's not forget that this is high pressure gas as the water encroachment maintain reservoir pressure. The bypassing takes place also on a macroscopic scale or reservoir scale. This hypothetical reservoir, where we have only one well, you can see that at the time water reached that unique well in the reservoir, significant amount of gas, high pressure gas, can remain up dip of the well. Co-production technique can be used to improve the recovery from such wells. Let's use this hypothetical reservoir to demonstrate that. We have two wells. Let's start producing gas from them at an appropriate rate. Due to this production, the gas-water contact will move up the structure, and usually when down-dip wells start producing high amount of water, that well is shut in. Co-production technique suggests that instead of shutting in the well, that we will use this well to produce water. And actually, we would like to maximize water production from these wells. For the sake of discussion, let's say that these wells can remove or bring to the surface all the water supplied by the aquifer. What will happen to the water contact is it will stop in its track, allowing the up-dip well to deplete the reservoir to lower pressure. In reality, that is not possible, but we can slow down the advance of the water contact with the same result. This technique was tried in the Eugene Island, Block 305, offshore Louisiana. As you can see, 4 of these 6 wells that were drilled from the B1 platform are in blue because they are either shut in or producing high volumes of water. This leaves only 2 up-dip wells, B1 and B5, to deplete the reservoir. We looked at this reservoir and did some studies that suggested that if we don't produce any water, the pressure will remain quite high. Actually, at the end, no significant depletion has been realized. If we produce water, you can see 2 effects. One, the reservoir pressure, which depicted here in dash, was reduced considerably, and also the life of the reservoir was extended significantly due to the postponement of the watering out of the up-dip wells. 124 BCF of gas was produced prior to 1984. If we continue to produce this reservoir conventionally, we can add another 47 BCF for a total recovery factor of 62%, which is not bad. If we start producing water, meaning applying the co-production technique, we can add 102 BCF of incremental recovery for a total recovery factor of 83%, which is significantly higher than what we expect from these type of reservoirs. Co-production reserves amount to 55 BCF of gas. Of course, the economics control the feasibility of a process. Here we are looking at the present value cash flow for the two processes, co-production versus conventional, at different gas prices. As you can see, co-production is more profitable than conventional at any gas price. Let's take a price of $5 per MCF. The difference of the present value between the two processes exceeds $100 million. Now let's put that in perspective. The total investment needed to start this project was a mere $1 million, which was needed to equip the platform to handle the increased volume of water production. This is the actual performance of this reservoir. The red line represents the gas, and you can see it reached a very low levels in the 80s. The co-production was implemented in 88, and you can see the effect of water production. If we look at this cumulative graph, we can clearly see that the actual incremental recovery of co-production that was started in 1988 is 10 BCF. That's completely different than the 55 BCF predicted, which was predicated on a start time of in 1984. The reason for this decrease is that aquifer didn't wait for us to make up our mind and start the process. The aquifer continued to encroach into the reservoir. So this process need to be studied and looked at and implemented as early in the life of the reservoir as economically and practically feasible. The last method I would like to talk about is the water flooding of low-pressure gas reservoirs. Low-pressure gas reservoir, which are volumetric reservoir, the performance of which can be easily demonstrated using the P over Z graph that we are all familiar with. The performance on this type of graph is linear. At a point in time, which is the first, the leftmost circle on the graph, that's where we are, let's say, now. If we continue to produce the reservoir as usual, the dotted line will define the depletion reserves as it hits the abandonment conditions. If we inject water, we can slightly maintain the reservoir pressure at a higher level, thus postponing this event of reaching the abandonment condition. And as you can see here, the water flooding reserves exceed the depletion drive reserves. The question is when to start. Should we start at this point? Should we have started before? Should we wait? This is an optimization problem that we didn't want to get busy with at this time. We wanted to introduce the concepts. So what we said, let us see what will happen if we inject water when we reach the end of the primary stage. It is at that point that we consider compression. So we're going to compare water injection to compression. If we inject water at a level and we can maintain the reservoir pressure, you can see the amount of water reserves depicted here by this rectangle. Should we use compression, the production rate will decrease, and we have the compression reserve depicted under the ever-decreasing flow rate. Now, compression could realize higher volumes. However, as you can see, the water flooding accelerate the recovery of the reserves, hence the economic advantage. There's another advantage that to water injection. Compression does not maintain reservoir pressure, and that explains the ever decreasing flow rate. This flow rate will reach a level where we cannot clean the well from the liquids. These liquids will load the well or kill it, and that would require frequent intervention or frequent workover at additional cost. Amazingly enough, this process was tried in 1970 in Duck Lake D1 Reservoir in Louisiana. This resulted in an additional recovery of 3.6% of original gas in place, or 25 BCF of gas, which is nothing to sneer at. We tried to find why this application was not repeated. We surmise that this is because of the high water requirement. Gas is highly compressible, and it would require a lot of water. However, there is economic sources of water, which include produced water, and which we have to cope with high amount of it, or dump flood from a nearby aquifer. Let's look at the comparison between compression and water injection in Godchaux Reservoir A. That reservoir contained 11 wells. 7 of these wells were converted to injectors, and to realize a semblance of a line drive. This is a comparison between the flow rate. In purple, you have the flow rate using water injection while maintaining reservoir pressure, and the yellow line represent compression. You can see that we need 26 years to recover the compression reserves. The water reserve can be recovered in 6 years, hence a much higher present value. We have to underline the fact that compression reserves exceed water reserves, water injection reserve, because of the bypassing of some of the gas by water. So economic analysis, economic comparison is a must. Here are the results of this comparison. The present value of using compression in the Godchaux Reservoir A is $91 million. If we maintain the pressure, we can increase it slightly to $98 million. This 98 was obtained when water is a cost. Now, if we operate this reservoir as a water disposal facility, and actually we get paid to take this water off the hands of our company or other operators, that present value increases dramatically to $198 million. In conclusion, I would like to state that the DDP process using air injection, Huff and Puff, the co-production technique, and water flooding of low-pressure gas reservoirs are technically viable improved oil and gas recovery methods. The economic viability of these methods will vary from reservoir to another as expected. However, these methods should be added to the list of reservoir management tools we have at our disposal. Thank you.